Welcome to our deep dive into the principles of agentic systems. In this video, we'll unravel the foundational concepts that power intelligent agents and multi-agent systems. We'll explore what agency and autonomy mean, how intelligent agents operate, and the architectures that make these systems so effective. By the end, you'll have a clear understanding of how agentic systems are shaping fields like robotics, AI, and systems engineering. Let's begin our journey by setting the stage for why agentic systems are so pivotal in today's technological landscape. This chapter covers the essential principles of agentic systems. We'll start by understanding the core ideas of self-governance, agency, and autonomy. Next, we'll review what makes an intelligent agent, examining their unique characteristics. We'll then explore different architectures for agentic systems, including deliberative, reactive, and hybrid models. Finally, we'll look at multi-agent systems, using a travel booking assistant as a practical example. By the end, you'll have a comprehensive overview of the basics and critical aspects to consider when building intelligent agentic systems. Agentic systems stand out due to their intricate decision-making processes. These systems optimize choices within specific contexts and challenge our traditional ideas of accountability and responsibility. They are the driving force behind innovation in robotics, AI, and systems engineering. By enabling new forms of automation and intelligent behaviors, agentic systems have transformed how we approach complex tasks. Let's explore how these concepts manifest in real-world applications, from autonomous robots to intelligent decision support systems. Agentic systems are making significant progress across various domains. In robotics, they enable autonomous robots to navigate complex environments and adapt to changing conditions, proving invaluable in manufacturing, exploration, and rescue operations. In AI, agentic systems underpin intelligent agents and decision support tools, enhancing efficiency in finance, healthcare, and transportation. Systems engineering benefits from agentic systems by enabling distributed adaptive networks like power grids and transportation systems. These examples highlight the versatility and transformative impact of agentic systems. Self-governance is at the heart of agentic systems. It refers to a system's ability to control itself autonomously without external direction. Such systems can make their own decisions, set goals, and regulate behavior based on internal rules and algorithms. They operate according to their own states and adapt when the environment or objectives change. Through meaningful interactions with their surroundings, these systems continuously evolve and improve, making self-governance a foundational principle for intelligent autonomy. Self-governance in agentic systems involves several key aspects. Self-organization allows the system to structure its internal processes without outside help. Self-regulation enables it to monitor and adjust actions based on feedback. Self-adaptation lets the system modify its behavior in response to environmental changes. Self-optimization means it can improve performance over time, and self-determination allows it to set its own objectives. Together, these capabilities empower agentic systems to operate independently and efficiently. The self-governance of agentic systems is made possible by integrating advanced technologies. Machine learning, knowledge representation, reasoning, and decision-making algorithms all play a role. These technologies allow systems to process information, learn from data, and make autonomous decisions based on acquired knowledge and current context. As a result, agentic systems can continuously evolve and adapt, becoming more effective in achieving their goals. Agency is the capacity of an entity to act independently and make choices. In both human and artificial systems, agency involves decisional authority, intentionality, and responsibility. Systems with agency can evaluate options, set goals, and are accountable for their actions. This means they don't just follow instructions, they make purposeful decisions that impact their environment and the outcomes they produce. Consider a travel booking assistant responsible for booking flights and hotels. This system demonstrates agency by analyzing flight availability, ticket prices, and user preferences, then making decisions to find the best travel options. The assistant is responsible for the outcome, directly impacting the travel plan and cost for the customer. This example shows how agency enables systems to act on behalf of users, optimizing results based on defined objectives. Autonomy is closely related to agency, but focuses on the degree of independence a system has. Operational autonomy allows a system to perform tasks without human intervention. Functional autonomy enables it to adapt actions to achieve goals in different contexts. Hierarchical autonomy defines how much decision-making power a system has within a larger framework. In AI and robotics, autonomy is crucial for systems that must operate independently, adapting to new situations as they arise. In our travel booking assistant example, the system demonstrates operational autonomy by booking flights and hotels with minimal human input. It also shows functional autonomy by interpreting user commands and adapting to preferences. The level of hierarchical autonomy depends on privacy settings and access to sensitive data. Importantly, autonomy doesn't mean the absence of human oversight. These systems operate within boundaries set by their designers, ensuring both flexibility and control. As agentic systems become more autonomous, ethical considerations become increasingly important. Designers must carefully decide how much autonomy to grant, balancing innovation with safety and accountability. Ensuring that AI systems align with human values and ethical principles is crucial, especially as they take on more independent decision-making roles. This ongoing challenge is central to the responsible development of intelligent systems. To illustrate agency and autonomy, let's look at a simple algorithm for a travel booking assistant. The agent is initialized with a name, goals, and a knowledge base. It can set goals, update its knowledge, make decisions, and book travel independently. This structure demonstrates how agency allows the agent to act on behalf of the user, while autonomy enables it to make decisions and execute actions without direct human intervention. Here's how the travel assistant algorithm works. First, the agent is named and initialized. It sets up a list of goals and a knowledge base for storing information. Functions are defined to add goals, update knowledge, and make decisions. The agent evaluates options and selects the best one, then proceeds to book travel. This process highlights how agency and autonomy work together, enabling the agent to act purposefully and independently. A Python implementation of the book travel function brings the algorithm to life. The function sets the goal, updates the knowledge base, makes a decision, and confirms the booking. The output shows the agent's state, including its name, goals, and booking confirmation. This practical example demonstrates how agency and autonomy are implemented in code, providing a foundation for more advanced intelligent agents. While the travel assistant demonstrates agency and autonomy, it has limitations. It cannot interpret plain text user messages or infer intentions from natural language. Instead, it requires specific inputs like airport codes. This highlights the need for more advanced AI techniques such as natural language processing to create truly intelligent agents capable of understanding and acting on user intent. An intelligent agent is a self-governed entity that perceives its environment and takes action to achieve specific goals. These agents range from simple rule-based systems to advanced models capable of learning and adaptation. Key characteristics include reactivity, proactiveness, and social ability. Intelligent agents can operate in diverse domains, from robotics to decision support and virtual assistants. Intelligent agents are defined by several key characteristics. Reactivity allows them to respond to environmental changes in real time. Proactiveness means they anticipate future needs and act accordingly. Social ability enables them to interact and cooperate with other agents or humans. These traits make intelligent agents versatile and effective in handling both simple and complex tasks. Beyond their core traits, intelligent agents may possess advanced capabilities. They can learn and adapt from experience, improving their performance over time. Reasoning and planning allow them to analyze situations and develop strategies. Autonomy and self-governance enable them to operate independently, making decisions without constant human supervision. These features empower agents to excel in dynamic, unpredictable environments. Agentic systems can be built using different architectural patterns. The three main types are deliberative, reactive, and hybrid architectures. Each pattern defines how the system perceives, reasons, learns, and acts upon its environment. The choice of architecture depends on the complexity of tasks, the need for real-time responsiveness, and the level of reasoning required. Deliberative architectures, also known as knowledge-based or symbolic architectures, rely on explicit knowledge representations and reasoning mechanisms. They follow a sense-plan-act cycle, sensing the environment, updating the knowledge base, planning actions, and executing them. These architectures excel at complex reasoning and planning but may struggle with real-time responsiveness due to computational demands. The sense-plan-act cycle in deliberative architectures involves four main steps. First, the agent senses and acquires information about its environment. Next, it updates its internal knowledge base. Then it uses reasoning and planning techniques to formulate a plan. Finally, it executes the plan, taking actions to achieve its goals. This structured approach is ideal for tasks that require deep reasoning and careful planning. Deliberative architectures are powerful for tasks involving complex reasoning, planning, and decision-making. They can handle uncertainty using probabilistic reasoning and belief revision. However, maintaining and reasoning over large knowledge bases can be computationally expensive, limiting their responsiveness in dynamic environments. To overcome these challenges, deliberative architectures are often combined with reactive components in hybrid systems. Reactive architectures or behavior-based systems provide immediate responses to environmental stimuli. They do not rely on complex models or reasoning processes. Instead, they map perceptions directly to actions using simple rules or neural networks. This approach enables rapid, robust responses, making reactive architectures ideal for dynamic environments where speed and adaptability are crucial. Reactive architectures are known for their speed and robustness. They can handle uncertainty and incomplete information, and their decentralized nature allows for parallel and distributed processing. Multiple reactive modules can operate simultaneously, leading to the emergence of complex behaviors from simple rules. However, they lack long-term planning and advanced reasoning capabilities. Despite their advantages, reactive architectures have limitations. They generally lack the ability to plan ahead or reason about long-term consequences. Their focus on immediate responses makes it difficult to pursue complex, multi-step goals. Additionally, many reactive systems cannot learn from experience, limiting their adaptability in changing environments. Hybrid architectures combine the strengths of deliberative and reactive systems. They typically feature a layered structure, with a reactive layer for fast, low-level responses and a deliberative layer for high-level reasoning and planning. This combination allows agentic systems to respond quickly to environmental changes while maintaining the ability to plan and reason about complex tasks. Hybrid architectures use several techniques to leverage both layers effectively. Task decomposition assigns subtasks to the appropriate layer. The deliberative layer can generate multiple plans, while the reactive layer selects and executes the best one based on current conditions. Memory-augmented planning and reflection enable continuous improvement, making hybrid systems robust and adaptable. Choosing the right architecture for an agentic system depends on the application's requirements. Deliberative architectures are best for tasks that require complex reasoning. Reactive architectures excel in dynamic environments needing rapid responses. Hybrid architectures offer a balanced approach, combining the strengths of both to create adaptable, capable systems. Multi-agent systems, or MASs, are a key area in distributed artificial intelligence. They consist of multiple intelligent agents that interact, cooperate, and coordinate to achieve collective goals. Each agent is autonomous, perceives its environment, and acts to meet its objectives. MASs are powerful tools for tackling complex problems that single-agent systems cannot handle alone. Multi-agent systems are used in a wide range of domains. In supply chain management, they optimize operations by coordinating suppliers, manufacturers, and retailers. In traffic control, MASs manage traffic flow and optimize routes. Robotics and manufacturing benefit from MASs by coordinating multiple robots. Environmental monitoring, distributed sensor networks, and intelligent virtual environments are other areas where MASs excel. The main advantages of multi-agent systems include distributed problem-solving, collective intelligence, and robustness. By distributing control among agents, MASs are resilient to failures and can integrate heterogeneous components. Their scalability and adaptability make them suitable for complex, dynamic environments where centralized approaches would struggle. A MAS is defined by several key characteristics: autonomy, interaction, adaptability, distributed control, scalability, heterogeneity, and decentralized data. Each agent operates independently, communicates with others, adapts to changes, and contributes to the system's overall effectiveness. This decentralized approach enhances robustness and flexibility, making MASs ideal for complex problem-solving. Interaction mechanisms are crucial for MASs to function effectively. There are three main types: cooperation, coordination, and negotiation. Cooperation involves agents working together towards a common goal. Coordination manages interdependencies and shared resources. Negotiation helps agents reach agreements on resource sharing or conflict resolution. These mechanisms enable MASs to tackle tasks that are too complex for individual agents. Cooperation is when agents pool their knowledge, resources, and efforts to achieve a shared objective. For example, in disaster rescue operations, multiple drones and robots cooperate to locate and rescue victims. By dividing tasks and leveraging specialized expertise, agents can solve problems more efficiently than working alone. Coordination manages the interdependencies between agents' actions. In manufacturing, for example, robots must coordinate to use shared resources efficiently and avoid conflicts. Coordination mechanisms include task scheduling, resource allocation, and conflict resolution, ensuring smooth and efficient operations within the system. Negotiation allows agents to reach agreements on resource sharing, task division, or conflict resolution. Agents make offers, counteroffers, and compromises to find mutually beneficial solutions. Techniques such as auctions, voting, and bargaining are used, depending on the problem domain. Negotiation is especially useful when agents have competing goals or limited resources. In the travel industry, MASs can represent airlines, hotels, car rental companies, and travel agencies. These agents negotiate flight schedules, room availability, and pricing to optimize travel packages for customers. By coordinating and negotiating, MASs can handle dynamic changes in demand, supply, and pricing, creating a resilient and responsive travel booking system. A MAS for travel booking involves airline agents, hotel agents, and a travel agency agent. The system compiles travel packages by gathering flight and hotel options, then presents them to the customer. Once a package is selected, the system coordinates bookings and updates pricing dynamically. This algorithm demonstrates cooperation and coordination among agents to achieve the common goal of booking a complete travel itinerary. The MAS algorithm starts by defining sets of airline and hotel agents along with a travel agency agent. The travel agency interacts with airline and hotel agents to compile travel packages. When a customer selects a package, the system coordinates bookings and notifies the customer of the outcome. The system also updates pricing dynamically, ensuring that travel options remain competitive and up to date. This MAS example demonstrates both cooperation and coordination. Agents work together to achieve the common goal of booking travel for the user. The travel agency agent coordinates with airline and hotel agents to build and book the best travel package. This collaborative approach leverages the strengths of each agent, resulting in efficient and effective travel planning. While the MAS travel booking system is effective, it still requires structured input such as city codes to operate. It lacks the ability to interpret user intent from natural language messages. This limitation underscores the need for integrating more advanced AI capabilities, such as natural language understanding, to create truly intelligent and user-friendly systems. In this chapter, we've explored the world of agentic systems and intelligent agents. We've covered the core concepts of agency, autonomy, and self-governance, as well as the main architectural patterns for agentic systems. We've also examined multi-agent systems and their interaction mechanisms. This knowledge provides a solid foundation for developing intelligent, autonomous systems capable of operating in complex environments. With a strong grasp of agentic system principles, you're now equipped to select the right architecture for your use case and conceptualize multi-agent systems. In the next video, we'll dive deeper into the essentials of agentic systems, further enhancing your ability to build efficient, intelligent solutions. Stay tuned as we continue our journey into the fascinating world of AI agents and autonomous systems.